picking up here with video number 2 of chapter 4 on carbon and carbon life. So what's really important from this, and just in general, if you've never really talked about organic chemistry before or organic molecules, really this diversity, this molecular diversity that we see in all organic compounds is going to come from the carbon skeleton and the various shapes and forms that we can get from those carbon molecules. So we can get anything from a chain of carbon bound together with single bonds. Okay, and they can be relatively short like ethane or propane, or they can be significantly longer, hundreds to thousands of carbons chained together. We can have them be more rigid. So these have a lot of mobility around these single bonds, but we can have the carbon chains be more rigid with double bonds in them. So that too is still within a chain, but we're going to see difference in how that molecule will respond to others, how rigid it is, how it's able to bend or not bend based on the bond type, whether we're talking about a single or a double or even a triple bond. Branching is another method. So instead of being a long straight chain, we can actually have branching coming off. And they don't have to be as simple as this T shape that you see here. We can have a cross shape, or we can even have this small chain and a chain coming here and then branching off of that chain and branching off of that chain and branching off of that chain, so that we actually get a very complex structure. The fourth option for carbon skeleton variation are rings, where we see the carbon actually form a ring and then we have branches coming off of those rings. They may be all single bonds to the ring, or we may actually see some double bonds in the rings as well, like we do here in benzene. So really, the importance that I want to emphasize here is that carbon skeleton variation really depends upon the carbons, what shape they're laid out in, and how they're bonded to one another. And that brings me to hydrocarbons. What you noticed on this last slide is all we had here were carbons and hydrogens. And that brings me to the definition of hydrocarbons. Hydrocarbons are organic molecules that consist of only carbon and hydrogen. Many organic molecules, like fats, will have hydrocarbon components, even if they aren't 100% hydrocarbon in nature. And these guys, the hydrocarbons that is, are fantastic in that when they undergo chemical reactions and we start breaking bonds, they tend to release large amounts of energy. And that'll be really important when we talk about how we're going to rearrange these bonds and how we're going to break down these molecules. Some chemical vocab that you need to grab a handle on. Isomers. Isomers are compounds that have the same molecular formula, C6H12O6, for example. But the way those molecules or those elements are put together varies. So the difference between, say, glucose and fructose, both C6H12O6, but very different in that the way that you arrange those 6 carbons, 12 hydrogens and 6 oxygens. So it's the arrangement. It's like having all of the Legos to build a set. Say you want to build a Lego motorcycle. And you can put all those Legos together and you can form a motorcycle, but perhaps you can put them together in a different manner and form a bicycle or form something else. So that's an isomer. Three different types of isomers that we'll look at: structural, geometric isomers, and then a third group called enantiomers. Enantiomers. So structural isomers have different covalent arrangements in their atoms. We'll take a look at that, I believe, in the next slide or two. Maybe we just look at enantiomers, I can't remember. Geometric isomers will have the same covalent arrangements, but they'll differ spatially. So they'll be spaced out differently, and then enantiomers are actually mirror images of each other, kind of like a chimer, if you've ever come across that word before. So here we go. There's images of each. So this is a structural isomer. I have the exact same chemical formula, Okay, I have 1, 2, 3, 4, 5. So I have C5, and I have 5, 10, 11, 12 H. But in this arrangement, and I have, yeah, I have pentane. If I have it in this arrangement, I have 2-methylbutane. So that's a structural isomer. These are geometric isomers, so they're built together the same way. It's just that I have a slightly spatial difference. I have a rotation here, so you'll notice that in this version of the geometric isomer, I have these unknown X groups on one side of the double bond. They're both up here. And in this version, that's in the cis isomer, and in the trans, they're on opposite sides of that double bond. They're sitting diagonally across that double bond. Here's an enantiomer. So I have an L isomer and a D isomer. Enantiomers are really important in the pharmaceutical industry. They really form that mirror image, can have very, very different effects on how that substance functions within an organic or organism. So, for example, I have ibuprofen. Ibuprofen, as you probably know, is used for pain and inflammation. It will block the site for the prostaglandin uptake. So I have a very effective enantiomer that's called S-ibuprofen. But if we take the exact mirror image of that, what I end up getting is a very ineffective enantiomer that's called R-ibuprofen, and it doesn't work at all. Same thing for albuterol, which is used to treat asthma. What it does is it dilates bronchioles. It reopens those airways that are constricting. And in the R-albuterol form, very, very effective. If we take that mirror image and have S-albuterol, isn't going to work at all. So very, very different in that regards. Um, Here's a great place for us to break this video. We're going to come back and we're going to talk about chemical groups that are going to branch off of our carbons and what that means for the overall molecule itself.